Alright guys, so let's think back for just a second back to stoichiometry in January. With stoichiometry we answered a lot of questions where I said I give you this much of this much of that, how much product do I make? And to answer that we had to find the limiting reactant. So we figured out which reactant runs out basically. And we used which one ran out to determine how much product we could make, right? So if I had a situation where I just have something simple like A plus B makes AB, if I had 3 of A and 4 atoms of B, how many ABs could I make? 3. And I'm going to run out of A. Okay, so A would be my limiting reactant. So this worked very well for us, so we did it for a long time. Did it with gases, did it with solutions. But this really typically just works for ionic reactions. Most reactions that involve covalent compounds typically do not allow one of the reactants to run out. Okay? So think about it in terms of efficiency. They aren't efficient enough to use up all of one of the reactants. So when we think about it from before, we could say we're going to make 3 ABs. But in fact, we might just make 1 now. Okay? So we'll talk about this chapter, situations where we don't use up all of one of the reactants. We have a situation where we make some product, but we don't use up all of our reactants. So now I have to figure out how to calculate how much product we're going to produce if we don't use up all of our reactants. So the idea this hinges around is that most of the reactions that we'll look at are reversible. So they can go in both directions. So we said that if A plus B is synthesis, going the other direction is what type of reaction? Decomposition. Okay? So we know that synthesis and decomposition are opposites of each other. Okay? So the question now is, if A plus B can turn into AB, and also AB can decompose into A plus B, what prevents when I make AB from it immediately decomposing? And the answer is nothing, because that actually happens. So I have to look at kind of the relationship between the forward and the reverse reaction. And that relationship is going to decide how much product we produce. So the big idea that we'll talk about is equilibrium. And the definition is typed out there. It says equilibrium is reached when the rate of the forward reaction equals the rate of the reverse reaction. So it says equilibrium is not when the reactions stop, it is when the two rates are equal. So the textbook gives a little analogy about a concession stand at a football game. And it works even better now with the whole COVID restrictions. So think about if you have a concession stand line at a football game. And because of some COVID restriction, the maximum length of the line is 5. So they have the little dots where you have to stand on. So 5 people in line. But a bunch of people want to go to the concession stand. So as soon as one person leaves the line, somebody else is going to do what? Join the line. Okay? Then when another person leaves, somebody else joins. So there's constantly going to be how many people in line? 5. But are the same 5 people going to be there for the whole game? No. Are people constantly leaving the line? Are people constantly joining the line? Yeah, but they're leaving at the same rate. Okay? As soon as one person leaves, one person enters. So as long as the rate of leaving and entering the line is the same, will the overall number of people in the line change? No. So the same situation applies here. As long as the rate of the forward reaction equals the rate of the reverse reaction, will the amount of product that I have change? No. So let's just make up a rate. Let's say A plus B goes to AB. Let's say the rate is 1 mole per minute. Okay, so every minute I make 1 mole of AB. But then the decomposition rate is also 1 mole per minute. Okay? So the two rates are equal. So every minute I make 1 mole of this, and every minute I decompose 1 mole of this. So our reaction's constantly happening. Yeah. Do they ever stop? No. But do the amounts eventually stop changing? Yes, if we're making 1 mole and decomposing 1 mole at the exact same rate, should the overall amounts that I have change? No. So let's look at kind of why this happens. So we can rewrite A plus B turns into AB. And I could have just as easily written it as AB decomposes into A plus B, so both ways happen. So let's think about when I first start this reaction. I'm going to take a scoop of A and a scoop of B and put it in a beaker and stir it, whatever I have to do. Okay? So initially, at the very instant that I start, when I mix together A and B, how much of the product AB do I have? None. Okay? 0. So what is the rate of decomposition at the very instant that I start? 0. Because what do you have to decompose AB? You got to have AB, right? You can't decompose it if you don't have it. But I have a large amount of A and B. So I can say initially the concentration of A and the concentration of B is high. Because I'm just dumping a lot of it together. So I have a large amount of A and I have a large amount of B. And my brackets mean concentration. Okay? So hopefully on the quiz you just wrote that high concentration relates to a what kind of rate? High. Okay? So what kind of rate would I expect to see with A and B here? If concentrations are high, they're going to react together quickly or slowly? Very quickly. So I can say therefore rate is high. Okay, so the higher the concentration of the reactants, the faster the rate. This should make sense to us. And my decomposition rate is 0. Okay, I have nothing to decompose. But then, as time goes on, as A and B react together, the concentration of A separate and B separate is going to do what? Go up or go down? Go down. Because I'm using up A and I'm using up B. So as they react together, they're being used up. So I can say the concentration of A and the concentration of B goes down. Okay? Simply because we're using them up. So as you use it up, you have less of it. So as the concentration decreases, the rate's going to do what? It's going to decrease. So it starts off really fast, then it's slowing down. So now at the same time, I can say also the concentration of AB is doing what? It's increasing. Okay? As A and B react together, I'm making more of AB. So now I can say the concentration of AB increases. So I have more of the product. So as I get more of the product, the rate for decomposition is going to do what? It's going to go up. So there I can say therefore decomposition rate so as you make more of the thing that's decomposing in the reverse reaction, the more quickly it's going to happen. And this is going to continue until what happens? So equilibrium is reached, which means the rates are equal. So it continues until rates are equal. Notice it did not say that concentrations are equal. I said that rates are equal. So by definition, when rates are equal, the reaction is at equilibrium. Do I have any way yet of solving for what the concentrations are? No, they do not have to be equal. If they were always going to be equal, then we're saying we're making half the product. That's not true. It varies from situation to situation. So now, at this point, does the reaction stop? No. Does the reaction continue to happen in both directions? Yes, but they happen at equal rates. So for every molecule of AB that I make, I break down one molecule of AB at the exact same rate. So it's important that you understand the reaction does not stop. But do the concentrations continue to change? No. The concentrations stay the same. Okay? Even though both reactions are happening, they're going to offset each other. Okay? So as soon as we make one molecule, we decompose a different molecule at the exact same rate. Okay? So most reactions we'll look at going forward are equilibrium reactions. We have some going in both directions. Now, ionic reactions are slightly different. The ones we looked at in the lab, with your double replacement lab, they are not equilibrium reactions. They are affected by a limiting reactant. They are not reversible. They go, then they're done, and it's over with. These are slightly different. Okay. So for the old type of reactions, the ionic reactions, you just mixed it together, and it was good. It made all the product until one of the things ran out. But with these type of covalent reactions, we don't see that happen. So we have to do things to the reaction to make it produce more and more product. So questions about that before we move on? So what we're talking about now is called Le Chatelier's principle. Okay, don't try and sound it out. He was French, it's Le Chatelier. And it's the idea that we typically use behind equilibrium. So the definition is typed out for you. It says if stress is applied to a system in equilibrium, and we'll define stress in a minute, the system will respond in a way that partially undoes the stress applied. It says, and I'll give you examples of stress. So think about it in terms of if you're in my class and you're wearing a jacket and it's 95 degrees in here, that could be considered a stress to you. Okay? And you want to undo that stress of you getting hot. So how can you undo that partially? Take off your jacket. Does that completely fix the problem? It's still hot, but did it partially compensate for what I did to you? Yeah. So reactions do the same thing. That's Le Chatelier's principle. If we do something to the reaction, they're going to compensate as much as they can to undo that stress or that change we did to them. So a couple of examples of what a stress might be for a reaction. The first is the addition or removal of a liquid or a vapor. So in simple terms, you add something to the reaction or you take something away from the reaction. Okay, that's considered a stress, adding or taking away. The second was the example that I used, increasing or decreasing temperature. So changing the temperature changes the reaction, then increasing the pressure. So to increase the pressure of a gas, what do we do to a gas? Decrease the volume. We'll come back to that one in a minute. And the last one says catalysts have no effect on equilibrium. So they are not considered here in the stress category. What do catalysts affect? Not equilibrium, but activation energy, which in turn affects rate. So they affect how quickly we get to equilibrium, but they don't affect overall the equilibrium. Okay. So I know that's a lot of words and it's probably confusing. Let's look at a few examples of how to apply this. Should make a lot more sense. So example one is a very kind of common sense example. You can probably answer it on your own pretty easily. So this is a closed system of ice and water is at equilibrium. So imagine you have something at 0 degrees Celsius. At 0, water does what? Okay, it freezes. At 0, ice does what? Melts. So we're going back and forth at equilibrium. So the forward and the reverse reaction happens. And it says the stress that I induce as I increase temperature. So we have the balanced reaction. Ice plus energy gives me water. And my arrows, as always, are kind of jacked up. So the question becomes, as I add this stress, is it going to cause the equilibrium to be shifted to the left or to the right? And what I mean by that, am I going to get more ice or am I going to get more water? So you can answer this on your own pretty obviously. Let's look at it though. So temperature corresponds to ice, energy, or water. Which one? Energy. Okay. So temperature is a measure of energy. So am I increasing or decreasing energy? Increasing. Okay. So the stress is adding something to the reactant side. So the reaction wants to undo that. Okay? So if I add energy, how does it undo that? Yeah, somehow decreases energy. So how does this reaction have the ability to decrease the energy? To use it up, right? So which way uses up energy? Going from ice to water or water to ice? Ice to water, okay? So if the reaction uses up some of the energy that I added to make water, did that partially alleviate the stress that I put on it? Yeah, because it used up some of the energy. Now, does that fix the whole situation necessarily? Maybe not, okay? But it does partially alleviate the issue that I created. So the question, the equilibrium of the system shifts to the left or the right? The right. To use up the energy added. So as it shifts to the right, I'm using up my reactants to make product. So it uses up energy, so it decreases the energy that I added. This is once new equilibrium established, the concentration of water will increase. That's a good follow-up question. The amount of ice does what? Increases or decreases? Decreases. The amount of water does what? Increases. So it's pretty obvious you increase temperature, you increase water. But does it make sense why, in terms of adding energy in the reaction, trying to use up that energy to compensate for the change that I made? Good. So look at number 2. This is an actual chemical reaction, so it's a little bit different. This is a closed container of N2O4. NO2 is at equilibrium, so there's the balanced reaction. The stress that is applied is I'm adding NO2. So I can fix my arrows. So am I adding a product or adding a reactant? Product. So I'm adding over here. So if I add NO2, in simple terms, how can the reaction fix that? What can it do to undo that? You can take away NO2, you can use it up, right? So if I add NO2, if the reaction uses up NO2, did it partially undo the change that I made? Yeah. So which way will the equilibrium shift? The left or to the right? The left. It says in order to use up the extra NO2. Yeah.
Is it always just the opposite of whatever side the stress is added to?
If you're adding something, yes, but there's other situations where it's not adding quite so simply. So let's think about why now. So the reaction going to the left has a rate, so we can call that rate 2. The reaction going to the right has a rate, okay? At equilibrium, what could I say about rate 1 and rate 2? They're equal, right? But as I increase the concentration of NO2, increasing concentration does what to the rate of the decomposition reaction? It increases it. So now, rate 2 is greater than rate 1. So am I still doing the reaction in both ways? Yes. One of them is just faster than the other. So now rate 2 is greater than rate 1. So I'm going to get more on this side, so I shift that direction. Does that make sense? Good. Let's look at another one. Okay. So a closed container of N2O4, NO2 at equilibrium. So here's one where we're not quite, let's look at 3 first, sorry. A closed container of H2O and is vapor at equilibrium, so I'm evaporating. And the stress is vapor is removed from the system. So now I'm not adding, what am I doing? Taking away. So if I take away vapor, how can this reaction compensate and try to undo the change that I made? You can make more vapor. So to make more vapor, does equilibrium shift to the left or to the right? The right. To restore more vapor. So my concentration of vapor, I'm going to make more. Is my concentration or amount of water going to increase or decrease? It's going to decrease. Okay? I have to use up water to make vapor. Okay? If I added water, would I see the same change or the opposite change? Same. So if I added water, the reaction would want to get rid of the water. So it would also shift to the right to compensate. Okay? So if I have a reaction where I'm trying to make more and more product, one way to do it is if I constantly remove product, can I get the reaction to make more and more of the product? Yeah. Let's try one more. So 4 is a closed container of N2O4 and NO2 is at equilibrium. The stress is that I increase pressure. So for gases, what do I decrease to increase the pressure? Volume. So I have a smaller volume. So imagine the space goes from this to that. How many moles of gas are on the left? 1. So 1 mole produces how many moles? 2. So what can better fit in a smaller space? 1 mole or 2 moles? 1 mole. So equilibrium shifts what way? To the left. Because the smaller number of moles can better occupy that smaller space. On the front it's typed out the rule. When you increase pressure, equilibrium shifts towards the side with the fewer number of gas particles. Okay? Oh, it's typed out right there too. Okay. Questions about those 4 examples? Okay. We'll stop there for today.